Hello everyone, welcome back to another lecture video in differential equation, and let us continue dealing with linear differential equation, homogeneous linear differential equation, and the auxiliary equation this time has imaginary roots. So we are done with distinct and real roots and also repeated roots. So we're now in the third part, which is imaginary root. So let's say you have a differential equation. Let's say it's in the differential operator form, f of dy is equal to 0. And we know that after this, we would obtain the auxiliary equation f of m is equal to 0. And then after solving for the root, uh, we would uh, we would find out, or we would come to the conclusion that the root of this auxiliary equation is imaginary. So let's say you have a plus and minus I plus b. Okay, so applying what we know with the letter a, the first part, which is distinct roots. Now we have two roots. Essentially, you have two roots, m1 and m2. Okay, the first root is, we would take the positive side. So a plus I is the imaginary number, square root of -1. And the second is a minus ib. So we have two roots, and therefore the solution would be c1 e raised to, so m sub 1, and m sub 1 is a plus ib, okay, mx, right? And then plus c2 e raised to a minus ib x. Okay, now before we proceed, let me introduce a formula here for e raised to a times ib, e raised to a plus ibx. Okay, and that is equal to e raised to ax times the quantity cosine bx plus I sine of bx. Okay, now of course, your e raised to a minus ib times x will be also equal to e raised to x times the quantity cosine bx minus, so instead of plus here, this will be minus I sine of bx. Okay, so if we will substitute that to our problem, or to our solution right here, this will now be simplified as y is equal to c sub 1. So this one is equal to e raised to ax times the quantity cosine bx plus I sine of bx plus c sub 2 e raised to a minus ib times the quantity. Our quantity x is e raised to ax times the quantity cosine bx minus I sine of bx. Okay, and if we will distribute c1 e raised to ax to this quantity, we will have cosine bx plus c sub 1 e raised to ax times I sine of bx plus c sub 2. Let me just write c sub 2 here. So we have plus c sub 2 e raised to ax cosine of bx minus c sub 2 e raised to ax times I times sine of bx. Now, these two terms has a common term, which is e raised to ax. E raised to ax cosine bx, and if we factor that term out, no, what would be left is c1 plus c2. Now, for these terms, the common factor is so e raised to ax as well, sine bx. So I included so let's say I just factor out this one without the negative sign, and what would be left is c1 times I, okay, minus c2 times I. So you could also factor out I, cosine bx, c1 plus c2 plus e raised to ax sine bx. So, I did not include I here to avoid confusion. But what we have here is uh, we could substitute c1 plus c2 as a new arbitrary constant, let's say c3, and I times c1 minus c2 can be c4. Okay, so the solution, okay, would now be, so this one, c1 plus c2 is c3, c3 e raised to ax cosine dx plus this one is c4, c sub 4 e raised to ax sine of bx. Okay, and this would now be the solution that we will apply if we are given a linear differential equation wherein the auxiliary equation would produce imaginary roots. Now, of course, if we will apply this to a solution, no, we will not write C3 and C4, but instead, no, C3 and C4 here are just with respect to the simplification that we made. But of course, if we are applying this to the problem, then this would be C1 e raised to ax cosine bx, and then plus C sub 2 e raised to ax sine of bx. Okay, so just take note of that, the changes in the arbitrary constant. These C3 and C4 are just with respect to the simplification of the problem. But of course, if we are applying, then we will just write C1 and C2. We'll use C1 and C2 instead. Okay, so let's apply this to our particular problem. So we have here, find the solution of the differential equation given. We have quantity d squared minus 2d plus 5 plus quantity y is equal to 0. So first, our auxiliary equation is m squared, okay, minus 2m plus 5 is equal to 0. Okay, is 1. So if we will solve for m for the root here, obviously we cannot factor. So we will apply the quadratic formula, which is, let me write that here, which is if you have ax squared plus bx plus c is equal to 0, then x is equal to negative b plus and minus square root of b squared minus 4ac all over 2a. Okay, so here our a is 1, this one is our a, this one is our b, so a, b, and c. So we have negative b, so that would be 2 plus and minus square root of b squared, so 4 minus 4ac, so 4 times 1 times 5 all over 2a, so that would be all over 2. Okay, so we have 2 plus and minus square root of b squared, so we will now evaluate this. This would be negative 20, okay, and then 4, so this would be 16, so over 2. Okay, so your square root of negative 16 would be 16 times I. Okay, 16 times, or let me just 16 square root of 16 times I. Okay, I will not be included because remember, I is already equal to the square root of negative 1. So let's simplify this. So we have 2 plus, this would be plus and minus 4 over 2. So 2 plus and minus 4i over 2. And then if we distribute 2, we'll have 1, okay, plus and minus 4 over 2, so that's 2. Okay, 1 plus 2i. So after solving for the root, okay, it's important to take note, okay, what is your a and b. Okay, so remember the solution or the roots that we have here in the derivation of our solution is we have m1 a plus ib and m sub 2 a minus ib. Okay, So that's important to take note. So A would be 1 and B would be 2. Okay? And then, let us apply this to this particular solution. So y is equal to c sub 3, or not c sub 3, c sub 1 e raised to ax, okay, cosine bx plus c sub 2 e raised to ax sine of bx, okay. So substituting a and b, we have c sub 1 e raised to ax, so that would be simply e raised to x, and then cosine bx, so that would be 2x plus c sub 2 e raised to ax, so again this is simply x, and then sine bx, so sine 2x. Okay, so that would be the final answer. Actually, your final answer could also be factored if you will factor e raised to x. So that would be c1 cosine 2x plus c2 sine 2x. Okay, so I will accept both of these answers. Let's go to the next problem. So we have next quantity 2d cubed minus d squared plus 36d minus 18 times the quantity y is equal to 0. So as I've mentioned before, you can use an online grapher to verify at what point will the graph intersect with the x-axis. Because at that point, particular point, you can know that that point is the root. Okay, so here, since this is 1, so therefore this is 1 half, or that this particular point is 1 half 0. So therefore, we can now see that 1 half is a root. Okay, so if we will apply our synthetic division, we have 2, negative 1, then 36, and then negative 18. And if we use 1 half as root, okay, so we have here 2, 2 times 1 half is 1. So we have here 0, okay, 0 times 1 half is 0. So we have 36, and then 36 times 1 half is positive 18. Okay, so after dividing 1 half, or after dividing m minus 1 half, then therefore this is the quotient. Okay, or it can now be factored. Uh, our, what do you call this, our auxiliary equation, which is, I forgot to write, f of m is equal to 2m cubed minus m squared plus 36m minus 18 is equal to 0. So that is our auxiliary equation, can now be factored out as m minus 1 half times a quantity, so 2m squared, and then plus 36. Okay, plus 36 is equal to 0. Okay, so we have m sub 1 here, which is equal to 1 half. And then we have 2m squared plus 36 is equal to 0. So 2m squared, let's say we solve for m, is equal to negative 36. So m squared is equal to negative 18. Then therefore, m would be equal to the square root of plus and minus negative 18. Okay, and if we simplify square root of 18, negative 18, so this will be plus and minus square root of 18i. Now square root of 18, this is 9 times 2, 18 is 9 times 2, and the square root of 9 is 3. So therefore, we have plus and minus, m is equal to plus and minus 3 square root of 2i. Okay, plus and minus 3 times square root of 2i. So we'll have m sub 2 is equal to plus and minus, or plus m sub 2 positive 3 square root of 2i, and m sub 3 to be negative 3 square root of 2i. Now, for this m sub 2 and m sub 3, okay, following the pattern of a plus bi, in this case a minus bi, our a, okay, our a is equal to 0, and b, okay, b is equal to uh, 3 square root of 2. Okay, so those are our A and B. So again, m sub 1 is equal to 1 half. Okay, so if I will now write the solution, okay, so first let's write the solution for the distinct root. So we have c sub 1 e raised to x over 2, and then this imaginary roots. So we have c sub 2 e raised to ax. So e raised to ax, a is 0, so e raised to 0. And then cosine bx. So 3 square root of 2x, and then plus c sub 3, again e raised to 0, and then sine 3 square root of 2x. So we can still do some simplifications. So c1 e raised to c1 times e raised to x over 2, e raised to 0, as we all know, is 1. Okay, so those are equal to 1. So we have c sub 2 cosine of 3 square root of 2x plus c sub 3 sine of 3 square root of 2 square root of 2x. Okay, and that would be the final answer. Okay, let's go to the last problem. Problem number 3. So we have quantity d to the 4th plus 8d squared plus 16 plus quantity y is equal to 0. So the auxiliary equation here is m to the 4th plus 8m squared plus 16 is equal to 0. So what we can see here is we could factor this out, m squared plus 4, right? M squared plus 4, and then squared is equal to 0. So we'll have m squared plus 4 times the quantity m squared plus 4 is equal to 0. And what we can see here is we'll have m squared plus 4 is equal to 4, is equal to negative 4, and another m squared is equal to negative 4, now based on the two roots. So we'll have here m is equal to square root of negative 4, so square root of negative 4, and that would be equal to 2i. Okay, so same here, we have m squared is equal to square root of negative 4, and then therefore m is equal to 2i. Plus and minus 2i, plus and minus 2i, because this is the square root, no? So we have plus and minus. So we have here a combination of repeated and at the same time imaginary. Now let's establish first that for both of our roots, no, your a is equal to 0 while your b is equal to 2. Okay, so let's solve this step by step. First, this one. Okay, let's put here number 1, and then this one is number 2, the repeated. Okay, so the general solution, no, we first consider this one. Okay, the first time m is equal to plus and minus 2i was present, so we have c1 e raised to ax, so that would be e raised to 0 cosine 2x, okay, plus c sub 2 e raised to 0 again sine 2x, and then the second time it repeated, so we'll have x, okay, times the quantity. Okay, so times the quantity, c sub 3, okay, again e raised to 0 cosine 2x plus c sub 4 e raised to 0 sine 2x. So notice that I did not put x here and then x squared here, because it was only the root plus and minus 2i was repeated twice, so therefore it should be only x. Okay, so if you will simplify that, we have c1 e raised to 0 is 1, so we have cosine 2x plus c sub 2 sine 2x plus, so we have x c sub 3 cosine 2x plus x c sub 4 sine of 2x. Now we could group the terms with cosine, like for this case, the first and third term as cosine. So we'll have quantity c1 plus x c3 times cosine 2x, and then the second and the fourth term as Sine 2x, we'll have quantity c sub 2 plus x, c sub 4 times a quantity sine 2x. Okay? And that will be the final answer. So thank you for watching.